This is Dr. S.P. Arsa from Mechanical and Industrial Department, IT Roorkee. I am going to deliver my lecture 39 on the course of Strength of Materials, and this course is developed under the National Programs on Technological Enhanced Learning. In this lecture, basically we are dealing with the strain energy due to the banding and associated with the numerical problems, and also we are trying to discuss some of like the Castiglianos Theorem, that if we have the strain energy, then what the exactly meaning of the complementary strain energy is there, and how the associated terms are there through which we can calculate both of the terms, strain as well as the complementary strain energy. But prior to the lecture discussion, we would like to briefly discuss about what we have discussed in the previous class. In the previous class, we mainly discussed about that if we have the structure, and in this particular strut or in like any of the kind of thing is there, like the column, and if any eccentric loading is there, then what the exact impact is there of that. So like in the previous lecture, we started with the eccentric loading in the strut, and we found that when the eccentric loading is there, then there is an additional curvature part is there in the strut, and due to that there is an additional bending moment is there. So we need to add that part. And we found that even at the beginning part, that means when it is started with the pin joint, we have like due to this eccentricity, we have like the deflection, and this deflection is being like incorporated in that. So whatever we discussed in the Euler theory of the strut or column under the elastic stability, we found that the Euler theorem is not perfect in terms of the theoretical way. So that's why like we incorporated the eccentricity in those terms, and we found that after incorporation of the eccentricity, or we can say in other terms, after incorporation of the curvature or the bending moment, due to that we found that we are more realistic way, and if you want to design the strut with consideration of the eccentric load, or due to the eccentricity, and due to that we have the bending moment, we are having a realistic like the results through which we can say that if we are applying those things with those particular conditions, means the P by E, or we can say the M by Z in the whole like the moment, we always have the safer design, and whatever the buckling load is coming, it will come in the realistic way. So that's what we discussed, and we found that there is a direct interaction is there of the applied load, and the this Euler crippling load is there when we are considering the eccentricity in those terms. Then the later part like of that previous chapter, we discussed about the three main forms of energy under the axial loading. The first one was there, that is the strain energy was there, and under the strain energy like what exactly the impact of the strain energy is there when the direct application of the load is there, and under the direct application of load the kind of deformation is coming. So the first one the first form of energy was that. The second form of energy under like up to the elastic region we defined as the modulus of resilience. So this is the standard form is there like when we are drawing like the stress strain curve, and we are only drawing up to like up to the elastic region, or we can say that in other terms that if we apply the load, and or the load application is there up to only the yield point or the elastic region, whatever the energy is being absorbed, or whatever the area under that particular linear stress strain curve will give you the modulus of resilience, and accordingly we can simply calculate the sigma yp square by 2e will give you the elastic energy within that. The third form of energy which we discussed under the tensile test was up to the rupture part, and that term is known as the modulus of toughness. So here when we are discussing about the stress strain term, okay, this relations, we found that there are the two main phenomena are there. One is the elastic and one is the plastic region, or we can say rather that one is the linear relations and one is the non-linear relations, and if you are going up to the rupture point, both regions have to be considered. So in the modulus of toughness we considered both the region, and whatever the energy is coming is being absorbed up to the rupture is simply given the modulus of toughness is there for that. Or rather we can say that the area under that particular curve right from beginning to the end of this curve will give you the modulus of toughness for this kind of material. And we found that in all three form of energy, the key point is the material property, that what kind of material which you have taken, because corresponding the stiffer part is coming, the corresponding deformation will come under those conditions. And also we found that the cross-sectional area and the applied load both have the equal importance for calculating the strain energy or modulus of resilience or modulus of toughness. And then lastly, you see we discussed about the numerical problem in the previous class, that you see if we have the different load conditions altogether, then how we can calculate the strain energy for that, and how we can calculate the modulus of resilience based on, you see, the this yield point limit. So you see, if you know the the strain energy, you can simply get the yield point, or if you know the yield point, you can get the strain energy up to the elastic region, or we can say that the modulus of resilience for that. And also if we can also solve the numerical problem based on, you see, up to the rupture part, you see, because in that we need to limit only up to the elastic and plastic regions, and then you see the corresponding the energy will come, because if you can calculate the area under that particular curve, it can simply gives you the modulus of this toughness, or we can say that whatever the strain energy there up to the failure, that will clearly can be easily calculated with the using of these terms. But again, in those terms also, the Young's modulus and the strain part up to the fracture, because you see E into epsilon r square by 2 will give you the modulus of toughness. So in you see in that term also, the Young's modulus of elasticity as well as the strain at the rupture point is both are having the equal importance in that part. So this is what you see we discussed in the previous class. So in this class, you see, again we are going to discuss about the main strain energy in the bending action. So that's what you see in the previous terms, only the normal action was there, but now here the combined loading is there. That means you see here the direct as well as the shear stresses are being present in that, and now we would like to see the strain energy phenomena in those actions. So now you see here, if the bending is coming, always a beam is there in our mind. So we have a beam, a simply supported beam is there, and then you see the loading conditions are there on the particular beam. So consider a beam AB which is subjected to a given loading, you see here. So in that we have the M, the value of the bending moment at a distance x from A. So you see the A and B are the two simply supported free points are there where the pinch joints are being acted, and there is a x distance is there from the this point A, and there is a point load is acting at exactly center point of that. And from the simple bending theory, the normal stress due to the bending alone is expressed in terms of that. So we would like to express those things, but prior to that, you see, we would have a feeling about that you see here under that what we have the two different regions altogether in this, and then under the bending action, you see, we have both the shearing action is this normal action is there, the normal direct stresses are there, as well as the shear stresses are there along with that. So with that, you see, now just go back to the bending theory, we have sigma by y is equals to m by I. So through which we can calculate the bending stress sigma, which is equals to m into y divided by I. Now substitute the above relations in this particular expression for gaining the strain energy. So we have the strain energy U, which is, you see, for entire beam the integration of sigma square by 2E into dV. So now you see, we know that the sigma is nothing but equals to m into y divided by I. So we need to replace that part. So we have the integration for entire domain of the volume. Integration is equals to integration into m square y square divided by 2E into I square into dV. Or we can say that simply we need to substitute that volume in that particular domain. So what we have dx, because the variation is there in the dx only, because sigma x is there in the axial form, into dA. So dA is the elemental cross area is there for that particular beam. So now what we have the m square y square divided by 2EI square, which is simply a function of x only. So you see, these are all the constant terms are there. So with that particular thing, now we are simply manipulating those terms in the strain energy part. So we have strain energy U, which is equals to integration of 0 to L m square divided by 2EI square, because it is a function of x alone, so that means the distance alone. So we are keeping with this 0 to L integration. And so what we have the two main integration part. One is with the distance terms, which is varying with the distance. So we have 0 to L m square divided by 2EI square, and the another form is integration of 0 to A, whatever you can say, the area part, y square dA into dx. So now you see here this middle part, which is y square dA within the area domain, represents the area moment of inertia, or you can simply replace by I also with this, and the cross sectional area about this particular neutral axis, because you see in which you see our main focus is on the dimensional property of that and what will be the center of like the mass is there through which we can calculate the cross sectional area. So based on that, now we can simply calculate the strain energy of this particular cross sectional. So what we have u is equals to integral 0 to L, because you see the m square y square divided by 2ei square was only the function of x. So again 0 to L m square by 2ei into dx is there, because y square into dA integration will gives you the I, and I will be cancelled out in that term. So now we can simply calculate the strain energy under the bending action, which is absolutely focused on what the bending moment is there and what is the flexural rigidity is there of that particular material. So these are the two key parameters are there through which we can simply say that how much energy can be absorbed or how much energy can be put in that particular material based on what the bending moment is applied part is there and what is the flexural rigidity, that means what is the material properties there of that. So u is equals to integration of 0 to L m square divided by 2ei into dx. So this is, you see, the form of the strain energy for the bending action. Now we would like to solve some of the numerical problem based on that. So you see here, first the numerical problem is, now we need to determine the strain energy of prismatic cantilever beam. So you see here we have a cantilever beam is there as shown in this particular figure by taking into account only the effect of normal stresses. So again you see here somewhat we can say that certain assumptions are there that only our main focus is on the normal stress component. So we are ignoring the shearing part here. So whatever the bending action is happened under the action of, you see, this eccentric loading or whatever you see, the normal stress are being formed and we need to calculate only the bending part. So look at this particular picture, we have a cantilever beam and it is being rigidly fixed at this particular wall at point B, and at point A we have a point load which is being acted on that particular part, and we have the total length of this particular prismatic bar, the cantilever beam is L. Now you see the bending moment at a distance x from this particular end A is simply defined, m is equals to minus p into x, because you see we simply taken as a certain distance from that particular point. So p into x will give you the bending moment, and now we need to substitute the above value of m in the particular expression of the strain energy which we discussed in the previous section. So what we have you see the strain energy u, which is equals to 0 to L p square into x square divided by 2ei into dx. So we know that what exactly because in the previous case we found that the total responsible parameters for calculating the strain energy is the flexural rigidity EI, so it is already there, and the second part is m. So we know that the bending moment is absolutely in this particular example is p into x, so m square is being replaced by this p square x square. So u is equals to integral 0 to L p square x square divided by 2ei into dx. Now you see within that particular frame of mind we have, you see, the total strain energy. If we integrate that part, we have u is equals to p cube p square L cube divided by ei. So you see here, because the x square dx will be x cube by 3, so you see here we can simply replace that part and we have, you see, the total terms are like this. So we have the strain energy in that. Again you will find that the strain energy in these kind of bending action also the responsible parameters, because we are only considering the normal stress component, so the responsible parameters are the load application and the flexural rigidity of the material. So this is one point. Now we would like to see the next question. Next question is again it's pretty simple, because the first one was there the cantilever beam. Now our main focus on the simply supported beam. So determine the expression for the strain energy of a prismatic bar AB, okay, for the loading conditions as shown in this particular figure, and taking into account only the effect of normal stresses due to bending. So again you see our main intention is to focus on this bending action only. We are simply ignoring the shearing action here. So whatever the normal stress component will come, we need to consider those components only. So evaluate the strain energy for the following values here. So here the values are given as the load P, which is acted at point from point A of the left end is 208 kilonewton. And the length, the total length is given as 3.6 meter, that means 3600 millimeter. the total cross-sectional area of the beam is given as 90 millimeter, 90 millimeter square, and then we have, you see, in that we have the B, which is equals to, you know, like 2.7. That means, you see, the total is 2700 millimeter. So we have both the distances, you see here, and then, you know, like we can simply, because we have the total L, we have the B, so we can calculate the A, and we can simply figure out that what is the point of location is there of the load. Then, you see, we know the material, so we can simply get the part E. E is nothing but equals to 200 gigapascal, and then, you see, once you know the cross sectional area, you can simply calculate the mass moment of inertia. So we have I, which is equals to 108 you know, like into 10 to the power 8 millimeter to the power 4. So that's what you see, through which we can simply calculate that part. Now come to this particular real feasible figure of that. What we have, you see, you know, like this simply supported beams are there. So over both of the simply supports, we have the reaction forces RA and RB of these at point A and point B, and you see the point load is acted towards the downward direction. So obviously, you see, we can simply get the moment, this bending moment diagram for that, for which, you see, first we need to calculate the reaction forces. So for first, the reaction forces at point A is nothing but equals to PB by L, because you see the distance is B is given to us. So you see here the load into distance divided by L, and then, you see, you know, like we can simply calculate the reaction at point B also, which is nothing but equals to PA divided by L. So with those consideration, once you get it, you know, like those reaction forces at point A and point B, now we can simply figure out that what will be the moments are there under the action of load P at point D. So with that, you see, you know, like we are considering the distance x at this particular point. So we have m1 and m2, these two bending moments are there, and we need to find out these m1 m2 with the different configuration. So bending moment, using free body diagram, you see now of the entire beam, we need to determine, you know, like the values of m1 m2 with the using of following relations. So first, as I told you, see, RA and RB is there, which can be pretty easily calculated by PB by L and for RA, and PA by L for RB. Now the portion AD, you see, which is, you see, the left hand portion of the particular beam under the, and it is under the bending action. So you see here the bending moment MA is nothing but equals to the reaction, you know, like this RA into the distance x, because it is acted at distance s. So we have RA into x, or we can say that PB by L into x, which is nothing but the M1. So now you look at this particular free body diagram of this. Now what is there? This RA is acted on the top one direction, and you see here due to this point B, it is acting in this direction. Okay, so the, you know, like this bending action is there, and due to that we just want to balance that part. So we have the bending action, you see, M1, which is just, you know, like going in the counterclockwise direction, and which has the value of PB by L into x. That means, you see, whatever the RA is acted towards that, or just opposing that part, so RA into x is there. So this is one form. So you see, through which we can now calculate the moment 1, which is nothing but equals to PBx by L. But the real phenomena is that, again, that when, you know, like the bending action is there, our main focus is that now you have the M1, so now you can calculate the U1 for this one. So correspondingly, you see, now if you go towards the, you know, like the another portion, that is, you see, the B to D. So dB portion is nothing but, you know, like is having the influence of the load P, which is towards the downward direction, and the reaction forces at the extreme end of B. So you see here with that particular, the bending moment at a distance of that B from, you know, like the free end of B is nothing but equals to M2 is there. So what we have the next bending moment M2, which is, you see, coming as the RA into x. So what we have PA divided by L into x. Or coming to the point, you see, now what we have now M1, which is nothing but equals to RA into x, M2, which is nothing but equals to RB into x, and with those inclusion of that thing, we have a real feeling about how the moment being transferred from this AD part to BD part. So with those, you see, now you can simply look at the free body diagram of this, then you will find that what we have this particular point, you see, the B at only the reaction forces are there on the top of direction, and at the free end we have, you know, like this particular the loads are there, which is just going on the topward direction, and corresponding, you see, the bending moment M2 is there, which is trying to oppose the reaction forces RB, which is nothing but equals to PA by L. and which is the main, like the responsible parameter is there, which is inducing the moment in that particular beam. So you see here this m2 is nothing but equals to like this rb into whatever the distance is there. So we have like the rb into x is the m2, and we have the v, which is the like the shearing part is there, because we are ignoring that part. So only we just want to see that how these like the bending stress is being distributed amongst like this particular beam under the loading actions. But our main focus is to calculate the strain energy for that. So you see here the strain energy is a scalar quantity, so we may simply add the strain energy of the portion of these two portion m1 and m2 is there, in which so AD to that of dB to obtain the total energy of the beam. So U is nothing but equals to U of AD plus U of dB. So now you see here simply like what we are going to do here, simply like we are simply segregated this particular beam into two different regions, right from 0 to A, for which you see only the point load is acted on the left hand portion, and you see the another region is there for 0 to B, in which you see the dB portion is there. So and 0 to S action is being influenced by moment m1, and 0 to B is being influenced by moment m2. So now you see here with the using of that moment equation for the strain energy, what we have you see UAD is being replaced by 0 to A m1 square divided by 2 EI dx, and UDB is being replaced by this integration 0 to B m2 square divided by 2 EI dV. With those things, you see now what we need to do here, we need to again replace that part. So here what we have simply taken out this 1 by 2 EI taken out, we have 0 to A PB by L, because again you see we need to replace that part moment, which is m1 is nothing but PB by L into x whole square into dx, plus 1 by EI is taken out. So we have 0 to B this PA by L into like the x whole square into dx. So you see after doing this particular simple integration part here, what we have finally, we have 1 by 2 EI P square by L square B square into like in the bracket itself, you see after keeping those values for limiting condition 0 to A and 0 to B, we have B square A cube by 3 plus A square B cube by 3, or you see by simply adding that part, you see, and taking out A square B square, we have like the strain energy within that component U is P square A square B square divided by 6 times EI L square into A plus B. Or we can say that you see A plus B is nothing but it's a total length of the beam L. So we are replacing that part, and we have you see the final strain energy for like under the bending action, where the simple point load is there at a distance A from the left end, is U is equals to P square A square B square divided by 6 EI into L. So you see here like simply we have all those values, we have value of P, we have value of A, we have value of B, E, I and L. So after like keeping those values in this expression, what we have the value of strain energy U, which is nothing but equals to 200 into the load 200 is there, so 200 into 10 to the power cube whole square, and then you see we have the A value 900 square, we have the B value 2700 square, and divided by 6 EI, you see all those things which we are simply keeping those values, and ultimately we have the total strain energy is 5.27 into 10 to the power 7 kilonewton meter. So you see here it is pretty straight, like the expressions are there for calculating the strain energy. Only we need to focus that when you see the bending action is there, so which area is influenced by which moment, and corresponding you see the moment which is like coming out, who is the responsible parameter for the moment. So you see in that case, you see in the just now which we discussed, the m1 is coming due to the reaction force Ra and m2 is coming due to the reaction force Rb. Then you see just after incorporating all those forces, we have a simple formula of U, and we can simply replace those values and get the final value of strain energy. So you see here, this is the part where like simple discussion was there about the strain energy due to the bending action. Now we have one more energy term that is known as the complementary strain energy. So you see here in one of the diagram I shown you that when we are drawing, you see the stress strain curve, we have the two main like the reasons are there. One reason is the strain energy, one reason is the complementary strain energy. So consider the stress strain diagram as shown in this particular way also. The area enclosed by the inclined line and the vertical axis is called as the complementary strain energy, and for a linearly elastic material the complementary strain energy and the elastic strain energy are same. So you see here, if we are applying the load and if we are going up to the elastic region only, then we will find that the real physical sense of the elastic strain energy and the complementary strain energy is the same. But if we are going in the nonlinear region, that means you see where if you are going in the plastic region where the permanent set of deformation is there, then things are real different. So here if you see in this particular diagram, what we have the elastic region, and this is up to the the yield point is there. We can simply see that even this particular region or this region, they have a similar kind of nature. So obviously you see whatever the energy which is being stored in terms of this complementary or the strain energy, they have the same value or they have the same physical sense in that way. But now you see, if we consider the elastic nonlinear prismatic bar and it is subjected to an axial load. So you see here there is some sort of differences are there. So the difference is like that, we have you see the sigma 1 and we have the epsilon 1, and in these terms you see we have that we have a slopy curves are there. So within this slopy curve, what we have you see the d sigma 1. Now if you are taking a simple element of this particular slopy, means the nonlinear term, then with that consideration, if we have you see a small segment d sigma 1 and d epsilon 1 in the sigma epsilon curve. So you see here, after focusing on that part, we could simply for check it out that you see under these particular region where you see the strain energy is there, and under these particular regions where the complementary strain energy is there, what you see the significance is there. So the new term which is coming as the complementary work is absolutely to be defined as you see the 0 to p, because the load application is there of the p, which we are limiting that part, delta 1 as you see what the deformation is there into dp1. Or we can say that the total work which is coming in that particular deformation is w star plus w is equals to p into delta. So you see here that the total work which is coming as the complementary plus the real work, and which is equals to or we can say which is responsible for the load application and corresponding deflection is. So here the things are when we are discussing about the nonlinear regions, we could easily figure out you see from this particular diagram that in the nonlinear region we have you see even if we are talking about this particular range, then the this complementary strain energy is somewhat different than this particular regions. So now you see in the particular geometric sense of this particular work is W star, which we were discussing about the complementary part, and the W because of the normal work done. Now if you simply look at that particular figure of the nonlinear nature of this load versus deflection curve, then we can simply figure out that starting from the 0, now we have you see the P1 curve, and within the P1 curve we have the delta 1 region. So whatever the deformation is coming or it is to be computed, it has you see the delta 1 due to the load application of P1. Now you see here, if you go up to the real P and the delta, we can simply see that it is simply covering the total this the area of the nonlinear region also, and in that now we have the two different the work done is there. This work done is simply for the strain energy is responsible part, and this W star is responsible for the U star, and this U star is the complementary strain energy. Okay, and then in that you see if you are considering a small segment dp1 which is responsible for you see the delta this deformation d sigma 1. So now we would like to simply set up the basic relationship between those. So come to that point, U star, and I told you that the W star, which is the complementary work is there, is responsible for complementary strain energy, is equals to 0 to P, because you see the limiting load is P, so 0 to P delta 1 into dP. Likewise, the complementary you see energy density U star is obtained by considering the volume element, because you see this is the domain is the volume for any kind of strain energy, and you see either the complementary strain energy is also having the same domain. So by considering the volume element subjected to a strain the stress sigma 1, and epsilon 1 in a manner analogous to the use the same the definition for strain energy. We have U star is equals to integration of 0 to sigma epsilon 1 into d sigma 1. So complementary strain energy is equal to the area between the stress strain curve and the stress axis. So here you see this is the key feature. So the complementary strain energy is always coming under the area of stress strain curve respective of the linear and non-linear, but the stress axis is there. So the domain here is somewhat different than the normal strain energy, because in the normal strain energy it is again you see the stress strain curve is there, but the domain, or we can say the main the reference axis is the strain energy axis, the strain axis, but here the main domain is the stress axis. And and that's why you see here the total complementary energy of a bar, which can be simply calculated on the basis of U star is equals to 0 to sigma epsilon 1 into d sigma 1. So here you see we are considering a really small difference of this sigma 1. So how the d sigma 1 is changing with the corresponding the strain is. So here our main focus for the complementary strain energy is absolutely focused on what exactly the variation is there in the elemental part of the stress, and then you see what the corresponding changes are there in the strain part. So you see here, after considering of all sigma small elements where you see there is a variation is there in the stress part, we can simply get you see the U bar by the integration. U star is nothing but equals to integration of all those volumetric part. So you see here for all complementary strain energy we found that the domains are somewhat different than the complementary strain energy and the this normal strain energy, or we can say the elastic strain energy. And that's why you see we were discussing about in the initial phase that if we are talking about the linear elastic region, then the complementary strain energy and the elastic energy this elastic strain energy must be same, because in that you see whatever the domain is there, they will simply have a linear relationship irrespective whether it's a strain domain or a stress domain, and since they have the proportional relationship, so there is no difference as such. But when we are talking about the nonlinear relationship, then you see both of the domain, means if you are talking about the strain, or if you are talking about the stress part, you see here they will provide the different domains altogether, and whatever the corresponding strain energies are there based on the deformation, they have to be a real difference in that sense. And that's why you see in the nonlinear relations we altogether we have different relations for this complementary strain energy and the elastic strain energy. Now we are going to discuss about the Castiglianos theorem, and the Castiglianos theorem is basically focused on the complementary strain energy and the elastic strain energy, in which you see if any slight change is there within the elastic region, then which energy is dominating. So coming to the strain energy technique are frequently used in analyzing the deflection of beam and the structure, as we discussed. So Castiglianos theorem are applicable to any structure for which the force deformation relations are linear. So that's what you see, I told you that if within the elastic region if any slight change is there, we can simply go with this particular theorem. So now consider a loaded beam, which I am going to show you on the next slide, and there are you see two main loads are there, P1 and P2, which are producing the deflection, two different deflections Y1 and Y2 respectively. So you see the strain energy within the beam is equal to the work done by the forces. Since you see we have the two different forces and both the forces are equally responsible for corresponding deflections, so we have the strain energy U is equals to half of P1 Y1 plus half of P2 Y2. So now coming to the figure, we can simply see that it is a simply supported beam, but you see here we have simply we are giving a kind of flexibility so that through which it can simply move in the axial direction. So when we apply the load P1 and P2, you see at the corresponding locations, we could figure out that we have you see this particular straight part is there, and we have you see the deflections are there, P1 Y1 corresponding to P1 and Y2 corresponding to P2. But if any slight change is there in the load P1, we know that there is slight change will corresponding coming in terms of you see the delta Y1 and delta Y2, because you see if addition or subtraction any kind of you see the variation is there in the P1, always deviate this particular position here. So if it is simply deviating this particular position, there is an additional phenomena is coming, which is you see coming as delta y1 and delta y2. So you see what the exact impacts are there of these things we are going to consider here. So let us say the load P1 is being increased by an amount of delta P1. So let delta P1 and delta P2 be the corresponding changes in the deflection, like due to the change of load delta P1. So you see here now we have the different the deflection terms are there because of like the additional load of P1, and which is considerable as delta P1. So you see the increase in the strain energy due to the additional part is nothing but equals to this delta U, which is you see the incremental part is equals to half of delta P1 delta Y1, because of you see like the additional P1 is coming from that particular part, and then you see due to this additional part what we have simply the additional deflections are there, delta y1 and delta y2. So you see the total part is P1 delta y1 plus P2 delta y2. So now you see we have the new term of the strain energy, that is the incremental form, is equation 2. Suppose the increment in load is applied to the first followed by P1 and then P2, then the resulting strain energy is somewhat different. That means you see here now we are increasing the load just at the P1 first, and then you see the simultaneous increase is there in the load capacity in the P2 also. So obviously you see the total like the strain energy is coming out as U plus delta U is equals to half of delta P1 delta Y1. Delta Y1 is coming due to the delta P1, so that's what you see it is like that, plus delta P1 and the delta P1 and the Y1 is there, plus P2 into delta Y2, and then you see half of P1 Y1 is there plus half of P2 and Y2. So you see here what we have several components altogether. The one you see because of the increase in load, so delta P1 is there, and due to this increase in load we have the increase in deflection. So you see the two different phenomena are there with the delta Y1 and delta Y2. And then you see the corresponding, you see like the P1 and P2 are equally responsible for Y1 and Y2 deflection. So these components have to be there in that particular inclusion. So that's why you see if you are computing the total strain energy, then you see we have almost all kinds of components in that particular expression. Since the resultant strain energy is the independent of the order of loading, you see whether it is first it is coming to the P1 and then it is going to the P2, or first it is coming to the P2 or going to the P1, it doesn't matter, you see. So the equation, you see whatever the equation which I have shown you here, it can be simply equated both the part, and then you see we can simply obtain delta P1 delta P1 into Y1 is absolutely equal to P1 delta Y1 plus P2 delta Y2. That means you see here even with the increase of load in the P1, it is simply responsible for having the displacement at Y1 location and Y2 location, and that's what the equation 4 is showing is. So you see here we can again say that delta P1 is coming, means there is an additional of load is there, and the P1 part responsible for P1 into delta Y1 plus P2 into delta Y2. And equation 2 and equation 4 can be combined, and we have you see delta U divided by delta P1. That means you see here the change in the strain energy with the change in the domain of the load is equals to Y1 plus half of delta Y1. That means you see here whatever the changes are there in the load formation, the corresponding changes will come in the strain part with the deflection original and with the slight change in the deflection. So that's what you see the equation 5 is telling. Or upon taking the limit of delta P1 approaches to 0, that means you see there is a very slight change is there in the load P1. So partial derivative I use because the strain energy is a function of both P1 and P2. So when we are saying that delta P1 is tends to 0, so you see here obviously the delta Y1 will be in a 0 in the equation 5. So we can say that the delta U divided by del P in the partial derivative term, as I told, because it is a function of strain energy part is there. So delta U by delta P is equals to Y1. So for general case, there may be, you see, the number of loads are there, and we can simply write this equation as delta U by delta Pi, because you see here we are saying that there are tons of loads are there, and due to that we have, you know, like the various segments of strain energy is there. So the strain energy within that particular domain, delta P1, so delta U by delta P1 is equals to Yi. So this is, you see, the equation is known as the Castiglianos theorem. So Castiglianos says that we have n number of deflections are there, and these are equals to the domain of the load with respect to their this strain energy. So du by dpi will be exactly equal to yi, means that the strain energy within the domain of all the loads, the summation of those things will give you the this deflection for individual point. So this is, you see, the like the Castiglianos theorems are there, and if you simply separate out these terms, then we'll have the statement. The statement of this theorem can be put, like as the follows, like if the strain energy for a linearly elastic structure, because again you see this is the first condition is there, that the Castiglianos theorem is only applicable to the linear elastic way where the stress is proportional to strain. So for a linearly elastic structure, it is the strain energy is expressed in terms of the system of external loads, means whatever the external loads are there, you see P1, P2, P3, P4, the partial derivative of strain energy del U with respect to concentrated external loads del Pi is the deflection of the structure at a point of application and in the direction of that load only. So you see here the partial derivative of the strain energy with respect to concentrated load will give you the direct deflection within that particular direction at a particular application. So this is the Castiglianos says that even you have number of loads, you can simply differentiate those things with respect to the strain energy, and they will give you the deflection of at those points towards the application of the load. And in a similar fashion, Castiglianos theorem can also be valid for like the applied moments and the resulting relations of the structure. You see, because he has given you like 4-5 theorems are there, but generally you see we restrict ourselves within those theorems. So you see here within those moment also we can say that the partial derivative of the strain energy with respect to the concentrated moment, not only the external load, with respect to the moment, concentrated moment for all those, you see, external moment applied, will always give you the resultant rotation of the structure at a point of application and in the direction of the moment only. So this is, you see, the another theorem. Again I am repeating the important, like the statement that the partial derivative of the strain energy with respect to the like the applied moment, it always gives you the resulting rotation of the structure at those particular points of application where you see the moments are applied in the direction of those moment only. So this is, you see, like with those moment we can simply get the resultant rotations, and you see if we are taking the strain energy with respect to the applied load, we have direct deflection. So you see we can simply figure out that what exactly the deflection is there and what exactly the resultant rotation is there based on what the applied load and the applied moment is. Now you see we are going for the first theorem again in a similar fashion as discussed in the previous section. The displacement of the structure are simply changed by a small amount of this delta, d delta, while another, you see, the displacements are simply like held constant, and there is an increase in strain energy is there, which can be simply expressed by du is equals to del u by del delta into d delta. So you see here what we are doing here, we are simply taking the small amount where you see the this d delta is there, and now we are simply taking that what exactly the increment is there. So if you look at this particular figure, then you will find that what we have a simple membrane here with particular like the basic, and when you apply the load here, like this vertical load, we have like this delta deformation is there, and within this delta what we have there is a direct increment is there in the strain energy, and this strain energy is simply computed on the basis of d delta. So with that, you see, now if you want to compute the strain energy, then this increase in strain energy is nothing but equals to du into this epsilon, this d delta, and then you see like since this is the domain of this du by d delta, and now we are going for all the small amount, so it is d delta is. So within that particular theorem, now we can say that this d delta by du by d delta is the rate of change of the strain energy with respect to that small deformation. And it may be seen that when the displacement the displacement di is increased by a small amount of this delta, work done by the corresponding force only, since within that particular displacement and other displacements are not being changed. So only we are simply focused on the small amount of d del I only. We are not considering the other displacements for that particular figure. So the work with which is equals to pi into d del I is always equal to the increase in strain, which is being stored in the structure. So we can say that the du is nothing but equals to pi, which is the responsible part, into d del I. And by increase in the simply rearranging those things, we can say that now using the Castiglianos theorem that the external point load can be easily calculated if we know that the increment in strain energy within the domain of the change in their displacement, or we can say that whatever the small amount of displacement change is there or increment is there in that domain, whatever the strain energy is coming, it will simply locate the this force application. So you see here in this chapter we basically discussed that if we have the two different domains are there, that means first of all, if we have the energy form, the strain energy due to the bending, then how we can simply figure out that under the action of the different forces, what are the different segments are there, and how we can figure out the strain energy component within that bending action. Then we were discussing about the different energy domains using the complementary strain energy and the elastic strain energy. And in that we found that these Castiglianos theorems are really important, because if we are talking about the externally applied load and there is a change, the corresponding changes are there in the strain energy, then the change in strain energy within the change in externally applied load will give you the displacement at that particular points, and these displacements are there within the load application point only. And similarly if you are talking about the another theorem, the Castiglianos part, then we will found that if the change in the strain energy is there within the change in the domain of bending moment, then we could easily figure out that how the angular rotations are being there within this del u by del mi, which will give you the theta. So you see here, with the arrangement of these two theorems, we'll find out that when we are talking about the small change in the strain energy within the domain of small displacement, straightway we will get the load at these particular points where the small displacements are there. So if you are talking about the first point, then du by d delta 1 will give you p1. If you are talking about the nth term, then we have pn is equals to del u by del delta n is there. So through that we can easily find it out that what the load applications are there at these particular points, which are equally responsible for the strain energy at this point and the displacement correspondingly. So that's what we discussed in these things, and Castiglianos theorems are really very important, where if we want to find it out the deflection or the moment at that particular point with the using of strain energy concept. Because in that the complementary form and the elastic forms are there, and as we discussed that actually within the elastic region, since they have equal, but if you are talking about this nonlinear phenomena where the plastic regions are there, then somewhat it is considerable in different terms as we discussed. So that is what we discussed in this particular lecture. Now in the next lecture our main focus is there, that now within those Castiglianos theorem, how we can really figure out those problems. That means how we can calculate the load conditions, or we can say how we can calculate the deformations within with the using of these strain energy concepts. So some of the numerical problems are there within that, and then we would like to conclude because the next lecture is the last lecture for whole of the course. So probably we are going to discuss about what we have discussed, because in the whole structure we have discussed many of the key points, and as this is the subject itself names as the strength of materials. So what is the physical justification of this course is within this particular limit, or we can say that actually what exactly the importance as a mechanical engineer or as a technocrat, what do you feel about this particular course, that whether it is really useful to study and in what sense it is useful. Because For many of the technocrat, they should know about, you see, the stress, what the meaning of the stress and strains are, and then you see if somebody wants to design some of the components, then which stress or strain components are really important to figure out those things. And then you see generally, like for many of the disciplines, the beam theory or the struts or the columns, or there are many other things, they are really important for designing part. And you see this strength of material subject will provide the basic input for all the kind of designs. So we are going to discuss in the next lecture all these terms. Thank you. Bye bye.